For this video, we'll be talking about Markovnikov's rule. So they have two rules. The first rule is the regular Markovnikov. So that means the positive element goes to the carbon with more hydrogens, right? Okay. Then we have the second rule is the anti-Markovnikov. This means the negative element goes to the carbon with more hydrogens, okay? So anti-Markovnikov is the negative element that goes to the carbon with the most hydrogens. And the same thing for the regular Markovnikov, but this time the positive element goes to the carbon with the most hydrogens. So they are opposite of each other. Now some may ask how to tell the difference. Well, we will show it here. For example, if I had this structure, okay, and we were asked to draw the product for this, right? The first thing I see is that this has a double bond, right? So Markovnikov is meant for alkenes, double bonds, right? So there's a double bond right there, and the double bond is attached to this carbon and this carbon. So we have two choices, right? Before we do that, we know that bromine is way more electronegative than hydrogen. So that means bromine will have a partially negative charge, while hydrogen will have a partially positive charge, right? So in this case, there's nothing written underneath, and this looks like a regular Markovnikov. So going back to our definition, the Markovnikov rule is that the positive element, the positive charge, will get placed on the carbon that has the most hydrogen. So on this carbon over here, you see that it has 1 and 2 hydrogens sticking out, compared to this carbon over here, where it has only 1 hydrogen sticking out. So that means that the hydrogen over here will go on this carbon over here, shown in our product section. So now this, the double bond goes away. We draw the hydrogen over here because the carbon has more hydrogen. And then we have no choice but to draw the bromine over here because we only had two choices, right? So this whole thing, it can be called as a hydrohalogenation reaction because we have a hydrogen and we have a halogen element. So another example, if we have the same structure, okay, we have the hydrogen and the bromine, but this time we have something underneath. This formula right here is called an organic peroxide. So when you see this formula over here, this will tell you this is an anti-Markovnikov problem. Okay, so this time we know that bromine is electronegative, so it is partially negative, and hydrogen is partially positive. Okay, the reason why this is bromine is partially negative because it has 3 lone pairs, right? The formal charge of bromine is neutral. But if we would determine which one is more negative and positive, we would say that bromine is more partially negative because it's more electronegative than hydrogen. So now in this case, underneath it has the organic peroxide. This means that this is an anti-Markovnikov. This means that the negative element charge will be placed on the carbon that has the most hydrogens, right? So this time we know that this carbon on the left, it has 2 hydrogens compared to the right where it has 1 hydrogen, right? So then we know that it will go on the left carbon. So we draw the reaction. Double bonds go away. The hydrogen will go over here, and we know that the bromine will be over here. Next example, we have this structure right here. We see that there's no organic peroxide underneath, so that means it's a regular Markovnikov. We know that hydrogen is partially positive, while bromine is partially negative. That means the hydrogen will go on the carbon that has the most hydrogens. So we know that the double bond is here. We always look for the double bond. That means it has to be either on this carbon or on this carbon. So when you look at this carbon over here, we see that it's connected to 1, 2, 3, 4, 4 groups. So there's no hydrogen. Compared to here, has 1, 2, 3, 3 groups, and the hydrogen sticking out. So then we know that it would go on this carbon. Double bond goes away, draw out the hydrogen, and we have no choice but to draw the bromine on the other carbon. For the most part, you don't have to draw the hydrogen. You should also already know actually that there is a hydrogen over here. So this will be the final product for this. Another example, we had this structure. It was reacting, adding with the bromine. This time it has the organic peroxide. This means they tell you that this is an anti-Markovnikov. So for this, we know that hydrogen is partially positive, and bromine is partially negative. That means that we look at the negative charge element, which is bromine, and we put it on the carbon that has the most hydrogens. In this case, the double bond is over here. That means the double bond, they would be placed either on this carbon or on this carbon. If we look at it individually, we know that this carbon has no hydrogen compared to this carbon over here, which has 2 hydrogens sticking out. That means it would go on here on this carbon. So the product for this would look like this. Bromine. And we know that the hydrogen would go on the other carbon looking like this. But we usually write that. We already know that it's there. That's the final product. Next example. The structure was added with this. And so for this, there is nothing underneath, no peroxide, so that means it's a regular Markovnikov. So this is a partially positive element, which this is a partially negative element. We look at the double bond and it's here. That means it is either on this carbon or on this carbon. This is a regular Markovnikov, so that means that the positive element will go on the carbon that has the most hydrogens. So if we look at each carbon individually, looking at this carbon, it has no hydrogens. But on this carbon, we see that it has 1 hydrogen sticking out. So in fact, it will go on this carbon over here. Redraw on the molecule. The double bond goes away. So the hydrogen will be sticking out like this. Okay. And the bromine would have no choice but to go on the other carbon. So over here. Again, you don't have to draw out the hydrogen. You should already know that it's there. So that is the final product for this. We have this structure, cyclohexane, and it was reacting with HCl. Okay. HCl has 3 lone pairs. The formal charge is negative, but it is way more electronegative than hydrogen. So this chlorine would have a partially negative charge, while this hydrogen would have a partially positive charge. So looking at the double bond, we know that it's here, and it can only be on 2 carbons, which is here or here. Looking at this carbon over here, we see that it has no hydrogen compared to this carbon over here, which has 1 hydrogen sticking out. carbon likes to form 4 bonds. So our product would look like this. The double bond will go away. You have the hydrogen sticking out over here. Then the chlorine would have no choice but to go on the other carbon up here. Okay, and then again, the hydrogen doesn't have to be drawn. It should already be known that it's there. It's our final product. Okay, let's do one more example. You had this structure, and it was combined with iodine, hydrogen and iodine. Okay, we know that iodine is way more electronegative than hydrogen, so that's why I get a partially negative charge, and then hydrogen will get a partially positive charge. So on this, there's nothing underneath. So this is a regular Markovnikov problem. So we know that the double bond is over here. Now it can either be on this carbon or on this carbon. So we'll look at each carbon individually. This carbon over here, it has one hydrogen sticking out, while this carbon over here has 2 hydrogens sticking out. So the one on the left and the one on the right is where the hydrogen will go. So our final product for this would be like that, while the iodine would be on the other carbon. Okay, and then again, you don't have to draw the hydrogen. It's better not to draw it because you already know that it's there. That's our final product for this. Now, after drawing the products, we will draw the mechanism for Markovnikov. So the mechanism are the arrows pointing what we will be doing. So the product was the final answer, but we got to show our arrows the steps between showing our products. So before we do that, we got to know something called a carbocation. So a carbocation is a carbon element that is positively charged. So we have 3 of these. The first one is a carbon connected to another carbon, right? And the rest are hydrogens, right? And this is called primary, okay? With a positive charge. Next, we have a positively charged carbon that has connected with 2 carbons, right? 2 carbons. And 1 hydrogen. It's called secondary. Finally, then we have a carbon that's connected to 3 carbons, okay? 3 carbons. Positively charged, and this is called tertiary. So we got 1 prime, 2 prime, and 3 prime, right? So stability goes this way. So that means this is the most stable. And this is where we want the positive charge to be on this carbon. When carbon is connected to 3 carbons, okay? It's connected to 3 carbons, that's where we want the positive charge to be on that carbon. So for carbocation, when drawing these Markovnikovs, we would want to have the positive charge on a carbon that has connected to 3 carbons, bonded to 3 carbons. And also, if you note, look at this, all these structures are trigonal planar. They all have 6 electrons and wanting 8 electrons. That means they're only bonded to 3 bonds, meaning 6 electrons, right? So now, drawing an example, our first example, we had a structure like this, and we said it was reacting, added with the bromine, right? Hydrogen and bromine. And we had to show the steps, right? We know how to draw the product for this, but now let's draw the mechanism, so the arrows. The first thing you want to know is to see where the double bond's at. We know it's there, so starting from the double bond, okay, it would go and grab the hydrogen, right? Or if you do that, bromine has 3 lone pairs. This double bond goes and grabs that hydrogen. The hydrogens, the bond connected to this electron, it goes to the bromine, okay? So then we will have a structure looking like this. So now we need to know where does the hydrogen go and what's the positive charge go? Okay, because when you lose electron, this carbon lost an electron, so that it'd be more positive. That means, where do we put the positive charge? So again, looking back at our rules, that the carbon should go on, the positive charge should go on the carbon that is connected to most of the carbons. So the double bond was over here. That means it would be on here, right? Looking at this carbon over here, it's connected to 1 and 2 carbons. Or compared to this carbon over here, it's connected to 1, 2, and 3 carbons. So more carbon is more stable for this. That means we have to put the positive charge right here directly on that carbon. All right, and then the hydrogen would go over here. We have no choice. Now after this, we would add the bromine, right? Don't forget about the bromine. Now it has, instead of 3 lone pairs, it has 4 lone pairs because it grabbed another electron and is negatively charged. Now what we do is grab one of the lone pairs on the bromine and attack that carbon that has a positive charge. So our final product would look like this. That is our answer for this. So the ending over here, this is our product, and the arrows pointing are the mechanism, drawing the steps that were between drawing the product. Okay, let's try another one. So if you have the structure, double bond. This is reacting with HCl. Chlorine has 3 lone pairs. Always needs to fulfill octet. Okay, neutral. So the first thing is, we look at the double bond. You see that it's here. All we do now is grab that double bond electron from that carbon and drag it. Well, not drag it, but grab that hydrogen. That hydrogen gives off the bonding electrons to the chlorine, which will give us a result of this. Redrawing the molecule. Double bond goes away, right? Now we need to know, where does that hydrogen and where does that positive charge go? Okay. We have 2 main points, this carbon and this carbon. This is because the double bond was on this carbon and this carbon, so it's the same thing. Looking at separately, on this carbon, we see that it's connected to 1, 2, and 3 carbons, as opposed to this carbon where it's connected to 1 and 2 carbons. So having more carbons is where the positive charge goes, because it'll make it more stable. It's more stable. So the positive charge would go on that carbon over here, right? And then the hydrogen would go on over here, has no choice. But then again, you don't have to draw the hydrogen. Only draw it so you guys can see it. But you should already know that there's a hydrogen connected there. Okay. This is added with C chlorine. Chlorine has 4 lone pairs now. Has a gain in electron, negatively charged. All we do now is grab one of the lone pairs that chlorine has. That electron goes and attacks that carbon that has that positive charge. So our product for this would give us something like this. That is our answer. Try another one. We had the structure. Okay, all we do now to draw this, we start from the double bond. It goes and attacks, grabs that hydrogen. That hydrogen electrons give off to that bromine. Okay. So the double bond goes and attacks that hydrogen. Oh. Now for this structure, is added with hydrogen and bromine. Okay, bromine has 3 lone pairs. Okay, so now that we always start with the double bond, the double bond would go and it grabs that hydrogen. While this hydrogen, the bonding electrons will give it all to bromine, right? And we have a product of this so far. But we need to know where does the carbocation goes, the positive charge for the carbon. See that the carbon, the double bond is on this carbon and on this carbon, because that's where the double bond's at. So that means it will be on this carbon, and on this carbon we would look to see where it will go. Going individually, we know that this carbon over here is connected to 1 and 2 carbons, while this carbon over here is connected to 1, 2, and 3 carbons. So more carbon is where the positive charge goes. So that's where the cation will go, on this carbon over here. So we add that carbon over here. Carbon will go over here. Okay. And the hydrogen will go over here. But then again, it's not necessary to write the hydrogen can bond to that carbon because it should already be known. So that's what we have so far. And this is all added to bromine, which has 4 lone pairs because they gain an electron as a negative charge. All we do now is start from the lone pair and go and attack that carbon that has the positive charge. So it would be here. So this will give us a product of this. Bromine over here, 3 lone pairs, and we have the methyl group over here. Okay. But as you can see something, we see that this carbon over here, it is connected to an ethyl group, a bromine, a methyl group, and a propyl group. Right? So that's 4 different groups. That means that carbon over there can be a chiral center. Right? That carbon is that carbon over here is a chiral center. So this carbon over here. But the only problem we have is that this bromine, it doesn't indicate if it has a wedge or a dash, right? Just a bond line, just a line, right? So this right here, this thing is called racemic mixture. So racemic is a 50% wedge and 50% dash. Okay, so we have an overall product of looking like this: a wedge on that bromine, and a dash on that methyl, and then redrawing that we have a dash on that bromine, and then a wedge on that methyl. So 50% wedge, 50% dash. This is how to do products and mechanism of Markovnikov.